Welcome to second lecture on unit 1, and in this lecture we will talk about inner product spaces. So, let us first revise what we discussed in the last lecture. In the last lecture we covered what are waveforms, we have looked into what is a signal space, we have said signal space will allow us to treat signals as vectors, and that will simplify digital communication a lot, because then we can treat signals as numbers. Okay. Then we have discussed what is L1 and L2 space, and we have defined what are indistinguishable functions, and finally we have defined what are basis vectors and linearly independent vectors. In today's lecture we will be talking about inner product space. Inner product space will allow us to talk about the length of vectors and the direction between the two vectors. Then we will define the inner product operation for L2 signals. Remember, L2 signals are the finite energy signals, right, and we are interested in L2 signals because in digital communication we usually transmit and receive L2 waveforms. Okay. Then we will prove that L2 space is actually an inner product space, and finally we will discuss how to do orthogonal expansion of a signal, which will also be really useful in understanding the transmitter and receiver designs. Okay. Okay, so let us get started with inner product space. So, remember in the last lecture we talked about the vector space, and in the vector space we said that for a valid vector space the addition of two vectors should be defined and the scalar multiplication should be defined, and there were certain properties which the vector addition and a scalar multiplication must satisfy in order for that operation to be in a valid vector space. But there was no notion of length and direction of the vectors, and in inner product we will be able to talk about the length and direction of vectors. Inner product is same thing as the dot product, okay, but for signals we usually do not say the dot product of signals, we talk about the inner product between the two signals. So, it is the same thing as what you studied in high school about dot product. Okay. So, inner product operation we will use the symbol to denote the inner product operation between the vector v and vector u. Now, as we have discussed in the last lecture, for a valid vector space certain axioms needed to be satisfied. Similarly, for a valid inner product space certain operations or certain axioms need to be satisfied. First, let us look what those axioms are. For an operation to be a valid inner product operation, Hermitian symmetry must be satisfied. What is Hermitian symmetry? It states that inner product of vector v with vector u should be same as inner product of vector u with vector v, but with conjugate. Hence, the order in which you do inner product matters. Remember, when we were talking about the vector addition, we said in vector addition the order in which you add vectors does not matter, but when we are computing the inner product the order in which you take inner product matters, okay, especially for the complex signals or vectors. Second is Hermitian bilinearity must be satisfied. What is Hermitian bilinearity? It is little bit difficult, so let me write. So, first condition is for an operation to be a valid inner product operation, if I am taking the inner product of vector alpha b plus beta u, where alpha and beta are scalars and v and u are vectors, with a vector w, then first of all linearity must be satisfied. So, what will happen because of linearity? We can write this as okay. Now, remember that we want also to take these scalars outside this inner product operation, and if these scalars are sitting on with the first vector they can be pulled out without any trouble. So, I can just take the alpha out, alpha is sitting with the first vector b v. Similarly, I can pull out this beta and I get this, okay, and this is this equation. Okay. Now, let us see what we mean by this equation. So, what does this state? If I want to take inner product of vector v with alpha u plus beta w. So, first invoking linearity, I can write this, and then now I have again to pull out these scalars, but remember now these scalars are sitting with the second vector, okay? And now if these scalars come out, they will come out with conjugate. So, this is the second equation. So, for a valid inner product operation, these two equations must be satisfied, and this is the notion behind Hermitian bilinearity. Okay. The third property now that needs to be satisfied for a valid inner product operation is, if you take the inner product of vector with itself, this inner product must be strictly positive. This can be equal to 0 only if the vector is a 0 vector. If vector is not a 0 vector, then the inner product of a vector with itself must be strictly positive. If the vector is a 0 vector, then the inner product of vector with itself must be 0. Okay. So, this is the meaning behind strict positivity. Now, these are the three properties that needs to be satisfied for an operation to be a valid inner product operation. Let us now take one example, and let us now see or assume that we have two vectors. Let us say that we have a vector v and we have a vector u, and this vector v is consisting of n complex numbers. It can be n real numbers or n complex number, does not matter, and vector u also consists of n complex numbers. Okay. Now, we have seen in the last lecture that we can think about vector as n tuples, where the vector can be thought as consisting of n complex or real numbers. So, the same ideas, we can think about the vectors as n complex or n real numbers. Now, if I have to take the inner product between the two vectors, I can define. So, this is by definition, I can define the inner product operation as this. So, it simply means that I need to pick up an element from vector v. So, let us say I have taken up the first element from vector v. I need to multiply with the corresponding element from vector u, that is u1 corresponding element, but this number comes with a conjugate, okay, and then I need to sum this up. So, I need to collect similar products and I should go on and on. So, this is what this equation represents. So, I need to multiply vi with ui conjugate, and then I have to sum this up for all values of I. So, this is by definition the inner product operation between two vectors, where vectors I am thinking as consisting of n complex or real numbers. Of course, if these elements are real numbers, then conjugate does not have any influence, but if they are complex, then of course taking conjugate makes difference. Now, if this operation has to be a valid inner product operation, this operation has to satisfy the three properties that we have listed out. So, Hermitian symmetry, bilinearity and strict positivity must have been satisfied. So, let us test, okay? Let us test whether this definition satisfy Hermitian symmetry. For this, I have taken the inner product of vector v with u, that this thing should be same as inner product of vector u with v, but with a conjugate. So, now let us see. So, I am interested in what is this inner product of v with u conjugate, and so v with u conjugate, it simply means that so inner product of vector v with u is this thing, and conjugate means that I have to take conjugate here, and conjugate of summation is nothing but the summation of conjugate. So, this thing is similar to v I conjugate and u I, and this is nothing but, by definition, this is the inner product of u with v. So, this is what we are saying, the inner product of vector v with u conjugate should be same thing as inner product of u with v to satisfy Hermitian symmetry, and this is what we have got. So, this definition looks right to us. Of course, we have to test whether the other properties are satisfied, and I leave that to you. Think about proving that other two properties are also satisfied if this definition is taken to define the inner product between the two vectors. Please work it out yourself. Now, let us define some other important quantities. First, let us define what is the norm of a vector. So, norm of a vector physically means that we are talking about the length of a vector. Length of a vector is an important quantity, and what is the length of a vector? Length of a vector is also known as the norm of a vector, and what is that? It is nothing but square root of inner product of vector with itself. So, you have to take the inner product of vector with itself, you have to take the square root of that thing, and that will correspond to the length of a vector. Okay. So, this is an important idea. How should we define the norm of a vector? Let us take an example for if this definition of inner product is adopted, what is that norm of a vector? So, I have to take the inner product of vector with itself, that means now u I should be replaced by v I conjugate, because inner product is with the vector itself, and what is v I conjugate? It is nothing but mod of v I square. Okay. So, you know that x into x conjugate is nothing but mod of x square if x is a complex number, you must have seen this. So, this turned out to be this. So, this is how the norm of a vector v will look. Okay. So, this quantity will correspond to the length of a vector. I also leave you with something interesting. Try to think, is this anyway similar to Pythagoras theorem? Try to think about this and try to get some intuitions. Okay. Let us move on. Now, it is the turn to define the angle between the two vectors, and this is one identity which I assume that you must have done. If I am interested in the cos of angle between the two vectors, this can be simply obtained by taking the inner product of with vector with another vector, dividing by the length of two vectors. Okay. So, this is how the cos of the angle between the two vectors can be thought about. Okay. Now, if I know this, I can define what is known as orthogonal vectors. What are orthogonal vectors? Orthogonal vectors are same thing as perpendicular vectors. You must have studied about perpendicularity in high school. So, orthogonality is the same thing as perpendicularity, but in engineering we rename things, we invent new names for the things that you have studied in school and make it look fancy. So, do not get confused, orthogonality is the same thing as perpendicularity. Okay. So, let us talk about the condition when two vectors are orthogonal vectors, okay, or perpendicular vectors. If two vectors are perpendicular, we know that the angle between the two vectors must be 90 degree, and hence cos of 90 degrees is 0, and hence this must be 0. Now, this can be 0 in two conditions, either the inner product of vector v with u must be 0, or the length of vectors must be infinite. But in this course we are not interested in the vectors with infinite length, we confine our discussion to the vectors which have finite length. In that case, when we are talking about the orthogonality, that can only be achieved if the inner product between the two vectors is 0. So, this is the test that you need to make to predict whether the vectors are orthogonal vectors or not. So, if you are interested in finding whether the vectors are orthogonal, you take the inner product between the two vectors, okay, and if it turns out to be 0, that means the vectors are orthogonal vectors. We can also prove what is known as Cauchy-Schwarz inequality. This inequality is very useful, and this inequality we will use a lot of time in this course. This inequality follows directly from this relationship. This is nothing complicated here. So, now we know that first let us do, we take the mod on both sides. So, let us take the mod on both sides. and now I know that cos takes a value between minus 1 and 1, the mod of cos must be less than 1 or equals to 1, right. So, this quantity is less than or equals to 1, and hence 1 must be greater than or equals to this quantity. Okay. So, if this is true, this implies that mod of inner product of vector v with u must be less than or equals to norm of v into norm of u, and this is the Cauchy-Schwarz inequality. When will this equality be satisfied? This equality will be satisfied when this quantity is same as 1, and when will this be same as 1? When the angle between the two vectors would be 0. So, that cos of 0 is 1. Okay. So, that means this equality would exist, this equality will exist only when this is 1, this quantity is 1, this will be 1 when the angle between the two vectors is 0. When angle between two vectors is 0, we say that the vectors are collinear vectors, they have the same direction. So, that the angle between the vectors is 0. So, this equality will be satisfied when v is some scalar times the u vector. Okay. So, let us look at the one dimension projection theorem, and here what we are doing is we are trying to break this vector v. So, we want to break a vector v into two components. One is a perpendicular component to vector u, and the other one is the parallel component to vector u. So, we are breaking down this vector v into two components, the one which is perpendicular component to another vector u, and one is the parallel component to vector u. So, this is like a right angle triangle. Okay. Now, what we are interested in is finding this v parallel to u vector, that is what we are interested in. So, let us see, if we want to find the length of v parallel to u. So, this quantity represents the norm or length of v parallel to u, that means we are interested in this quantity, this is length of v parallel to u. This can be obtained by first having the length of v vector, which is this. So, this is the length of v vector multiplied by cos of theta, where theta is the angle between vector v and vector u. So, cos of theta, as we have seen already, is this quantity. So, length of v parallel to u is given by this. Now, we can cancel the norm of v with norm of v, and we get this quantity. Now, finding the v parallel to u, we have to first take the magnitude or length of v parallel to u, which as I have said is this quantity, and then I have to multiply with the direction of v parallel to u. Now, if you look, v parallel to u has the same direction as vector u, and thus I have to multiply it with vector u, but I have to multiply it in such a way that this does not alter the length of v parallel to u, which we have already obtained. And the way to do this is by multiplying it with a unit vector. So, this is a unit vector. Okay. The one easy way in which you can obtain an unit vector is just have the vector and divide this by the length of the vector. So, this is the unit vector. Now, from this we get v parallel to u is this thing. It is a very important result, and thus I write it again. V parallel to u is given by inner product of v with u divided by norm square of vector u times vector u. So, this is v parallel to u. Now, if you have obtained v parallel to u, it will be straightforward to find v perpendicular to u, which will be given by the difference of v vector minus v parallel to u vector. So, this is this. Let us try to look at how can we define the inner product for L2 signals. Okay. So, let us get started by assuming that I have a vector v and I am trying to approximate this vector v in terms of another vector u, and c is some scalar. The angle between vector v and vector u is theta. Now, because vector v is not same as vector c u, there is an error in approximation, and this error is given by the difference between vector v and c u. For example, in this case I have shown that this error vector is perpendicular to vector u. Error vector in general can take any angle with vector u. Here for simplicity I have assumed that error vector is making an angle of 90 degree with vector u. Now, if you see carefully, if error vector was making any other angle other than 90 degree with vector u, for example, if it was making an obtuse angle with vector u, or if it is making an acute angle with vector u, whatever angle it makes other than the 90 degree, then the error vector would have been larger. So, the minimum value of error vector would happen when error vector makes an angle of 90 degree with vector u, and when this error vector makes an angle of 90 degree with vector u, the component of v along u is nothing but v parallel to u. This we have seen in the last slide. When we have a kind of a right angle triangle, this component of v along u is nothing but v parallel to u, and hence the component of v along u is nothing but it is v parallel to u, and as we have proved in the last slides that this value of v parallel to u is given by this quantity. If I try to think v parallel to u is some constant times u vector, then the value of constant is given by this thing. So, c, which is the value of the constant, is the inner product of v with u divided by norm square of vector u. So, this value of c will lead to minimum error in approximation when you are trying to approximate a vector in terms of another vector. Following from the same idea, let us try to do this exercise in the case of signals. So, we are now doing it in the case of vectors. Let us see if we do a similar thing in case of signal, what happens. And for this discussion, first I will assume that the signals involved are real signals, because this analysis is relatively simple in the case of real signals. So, I start by approximating a signal x t in terms of a signal y t. C is some constant, and the idea would be, let us find out what is the value of c for minimum error. So, because I am approximating x t in terms of y t, again I will have an error signal. Error signal will be nothing but it is the difference between the actual value of the signal and estimated or approximated value of the signal. If I know this is the error signal, I can also talk about the energy in the error signal. Energy in the error signal will be nothing but this quantity. You know that energy of the signal is nothing but this, right, and the signal error signal is this. So, energy in the error signal is this quantity. Please see that this energy in the error signal depends upon the c, value of the c, and what we are interested in, the value of c, for which the error signal is minimized. That means the energy in the error signal is minimized. Okay. For L2 waveforms, what is most important is the energy, okay, and that is why we are trying to see for what value of c the energy in the error signal is minimized. To do that, we can differentiate this quantity with respect to c, and when I make this derivative equals to 0, I can obtain the value of c. So, I differentiate this with respect to c, this quantity, what I would get is 2 times x t minus c y t into y t, okay, and I can keep this thing equals to 0, and from this I can obtain the value of c. So, let us see what is that value of c. If I want to put this as 0, let me do this. So, I had this integration 2 times x t y t dt is same thing as 2 times c y squared t dt, and from this I can take the c out. C is not a function of time, it can be pulled out. From this I get the value of c as this quantity. So, this is the value of constant that will minimize the error in approximation. Now, for equivalence between vectors and real signals, we can look in here. For vectors, we have already obtained that the value of constant that obtains the minimum error in approximation is given by this quantity. So, C is inner product of v with u divided by norm square of u. For the case of signals, we have got this value of C, which minimizes the error in the approximation of two signals. That is, when you want to approximate x t in terms of y t, this value of constant minimizes that error in approximation. Okay. Now, if we want to define the inner product for signals and we want to treat the signals equivalent to vectors, this will give us some hint on what is the good definition of the inner product. For example, we can choose the definition of inner product for the signals like this, because for vectors this thing is same as this thing. So, this is the definition for the inner product between two signals. Remember that the signals involved here are real signals. Similarly, if I want to equate denominator by denominator, then I get that the norm square of a vector is nothing but it is this quantity, and this quantity is nothing but it is the energy of a signal. So, energy of a signal is nothing but it is similar to norm square of a vector, and norm is length. So, energy of a signal is nothing but it is very similar to the length square of a vector. So, if you want to treat signals as vector, the energy is length square. Okay. Now, let us do the same exercise for complex signals. The idea is similar. We have a complex signal and we want to approximate it in terms of another signal. So, we are approximating x t in terms of y t, where x t and y t are complex signals. The error signal definition is same as before. Error signal can be obtained by taking a difference between the two signals. Energy in the error signal is also same as before, but because now the quantities involved are complex, we need to take a mod in here, and that complicates the thing. Okay. Now, we can also use an identity that mod of x square is x times x conjugate. So, from this what we can do is we can express this thing as this is like x and x conjugate. Now, what we can do is we can multiply term by term. So, we can multiply x t with x t conjugate, this is this here. We can multiply c y t with x t conjugate, this is this. Now, we can multiply this x t with this term, x t with this term, and finally, we need to multiply c y t. So, this with this, which would give us this. So, we will get 4 terms, right, in the multiplication. So, this is the expression that we have obtained from the last slide. Let us try to rewrite this equation in a different form. Let us write it like this. So, this is a more convenient way in which I want to express this. Why is this more convenient? We will see this soon, but let us assume that I want to write this into this form, and let us try to see whether this is equivalent to this. Okay. So, now if you see carefully, this is of the form of mod of a minus b whole square, and mod of a minus b whole square is nothing but it is mod of a square plus mod of b square minus a b conjugate minus a conjugate b. Now, a is this thing and b is this quantity. So, mod of a square is this quantity. So, this is mod of a square mod of B square is this quantity minus A B conjugate is this thing. So, A is C root E y and B is 1 by root E y, and I have to take the conjugate of this. So, conjugate will come here and here there will be nothing. So, this is A B conjugate, which is this quantity. Similarly, I can obtain A conjugate B as this. So, when I am expanding this, I get to this form. Let us see if this is equivalent to this form. So, this part is present in this expression, this part is also present here. So, we have mod A square also available here. This part is missing in this expression. So, this is not present. Is this present? A B conjugate is present. Yes. So, this is present here, and this part A conjugate B is also present here. So, this is same as this thing, but other than this term. So, we have to subtract this so that I make this expression same as this expression. So, let us try to do this. So, subtracting this term, we get this expression. So, now these two expressions are equivalent expressions. Okay. So, we will be using this expression rather than this expression. So, let us rewrite this. So, energy in the error signal we have just shown can be expressed like this. Now, we have to choose the value of C for which this energy is minimized. This term is not a function of C, this term is also not a function of C. So, we have to choose a value of C for which this term is minimized, and this term will be minimized when this term goes to 0, because this is a positive quantity, right. So, minimum positive quantity would happen when that quantity is 0. So, we have to choose a value of C for which this term goes to 0, and that value of C can be easily obtained if I substitute this as this. Okay. So, from this we can get the value of C, which is this value, easy, right. So, for complex signals this should be the value of C which needs to be chosen if I want to express one complex signal in terms of another complex signal. And let us now do the same thing as we did for real and vectors. Let us see what is the equivalence between vectors and complex signals. So, in the vectors, remember the value of C that minimizes the error in approximation when you wanted to approximate a vector in terms of another vector. This was the value of the constant that was giving us the minimum error in approximation. In case of signals, this is the value of constant that gives us the minimum error in approximation. And again, if I want to equate these two C's, and if I want to think the equivalence between numerators and denominators, I can get the definition of inner product for signals given by this expression, where the inner product of the signals can be obtained by multiplying a signal with the conjugate of another signal and then integrating this up. Again, this in the case of the complex signals corresponds to the energy of the signal, and as for the real signals, energy of a signal is nothing but length square or norm square of a vector. Okay. So, these are some ideas which will help you to think about what is the energy of a signal, what is the length of a signal, and what is the inner product between the two signals. Okay. So, finally, we can define the inner product for L2 waveforms. So, inner product of L2 waveforms can be defined like this, where you take in a signal or a waveform, you take in the conjugate of the another signal or waveform, and you do the integration from minus infinity to plus infinity. I can take the inner product of the signal with itself, and nothing happens other than that instead of Vt you need to have Ut, and this is nothing but energy of the signal, and this quantity would be same as the length square. So, if I am interested in length of a signal, trying to think about treating the signal as vector, then easily I can take this term, square root of this quantity. So, this will tell me what is the length of my signal. Okay. Now, because I now can treat the L2 waveforms as a valid inner projective space, even though I have not tested whether this definition satisfies all axioms of valid inner projective space, but we will do this. But let us start by assuming that these definitions are valid. These will allow me to do things like I can talk about now what is the angle between the two signals, what is the length of the signal, what is the length square of the signal, and so on and so forth. So, the next question that we need to ask is whether this definition corresponds to a valid inner product space, okay? And for that we need to test it through axioms that we have already seen. Hermitian symmetry must be satisfied, bilinearity must be satisfied, and strict positivity must be satisfied. But before all of this, one thing that needs to be checked is whether this integration always exists, right. If ut and vt are valid L2 signals, that means the signals with finite energy, is this integration always converges? Otherwise, you cannot define the inner product between the two signals. So, that is what we have to check. So, for convergence, what we need to do is we need to check whether the mod of this quantity is finite. That is when the integral exists. We have already seen this in the first lecture. Okay. So, for this to happen, we can also find out an equivalent expression that this should be satisfied. So, just replacing the Vt conjugate with Vt, right. The mod of a complex quantity or a real quantity is one and the same thing. Now, we have to check under which condition this is valid, okay. And for doing that, the idea is very simple. We can use the identity from the complex word. So, you know that alpha minus beta whole square is greater or equals to 0, and from this we get alpha beta is less than or equals to alpha square plus beta square by 2. Now, if I assume that alpha is mod of u t naught and beta is mod of v t naught, what I can say is that mod of u t naught, so mod of u t naught times mod of v t naught is less than or equals to this quantity, and mod of u t naught into mod of v t naught is nothing but it is mod of u t naught into v t naught. Okay. So, from this I get this, and then I am integrating this for all values of t naught. That means t naught is really the t, where t spans from minus infinity to plus infinity. I can get this expression. Now, because my signals involved are L2 signals, I know that this quantity is a finite quantity, this quantity is also finite quantity, sum of two finite quantities is a finite quantity, and hence this will be always a finite quantity, and hence this proves that the inner product for L2 signals is always defined. That means, if you have a finite energy signal, if you have another signal as a finite energy signal, if you want to find the inner product of these two signals, is always defined, is always finite. Okay. Now, finally, we have to test this definition through the axioms of inner projective space. Okay. So, first is we need to check whether the Hermitian symmetry is satisfied. Now, for Hermitian symmetry to be satisfied, we know that inner product of v with u should be same thing as inner product of u with v, but with a conjugate. Now, by definition we have chosen that the inner product of the two signals is this by definition. So, let us see what happens if I take a conjugate. So, conjugate of integration is nothing but integration of conjugate. So, this conjugate gets inside this integration ut conjugate vt dt, and this by definition is inner product of a signal v with signal u, and hence Hermitian symmetry is satisfied. Again, I will not do the proof of a Hermitian bilinearity, the proof is simple. I will request you to do and carry out this proof yourself. So, this is the third property which we have to see, and this property is about strict positivity. Strict positivity tells me that if I take the inner product of vector with itself, this should always be greater or equals to 0. This is 0 only if vector involved is a 0 vector. For the case of the signals, what it would mean is, if you take the inner product of the signal with the signal itself, then this should also be a positive quantity. It can only be 0 if the signal involved is an all 0 signal. That means, this should be 0 only if the signal is all 0 signal, but you know that this can be 0 in the case of L2 waveforms even if the signal is not all 0 signal. For example, we have seen that if I have a signal like this, so this signal is taking values only at discrete instances of time, then also for this signal, if you do mod Vt square dt, this will be a 0, right. This will be 0 because there is no width involved in these points, and hence when you pass this through an integrator, you will get an all 0 thing, right. So, for L2 waveforms, this is not satisfied. So, how do we get rid of this? We get rid of this by saying that okay, the vectors in L2 space need not be functions, but they are equivalence classes. What I mean by equivalence class is, all indistinguishable functions belong to the same equivalence class. For example, if I have a signal like this, or if I have a signal like this, or if I have an all 0 signal, all these signals, because they are indistinguishable functions, they belong to the same equivalence class, and let us say they belong to the equivalence class of 0. So, if I say that these Vt's are not functions, but equivalence class, then this thing can only be 0 if the equivalence class is 0, and hence we get rid of this mathematical subtlety. So, this is just to convince mathematicians and to satisfy axioms that we say that vectors in L2 space are not functions, but they are equivalence classes, right. All indistinguishable functions belong to the same equivalence class, right. But for engineers, do we have to worry about this? Answer is no, because out of this equivalence class only one function would be practically realizable. Thus, whether you call the L2 vectors as functions or equivalence class, it does not really matter. Now, we are moving to the last but probably the most important idea, that how can we do the orthogonal expansion of a signal. Let us start with vectors. So, let us assume that I have vector x, and I can express this vector x in terms of orthogonal components, right. For example, I can decompose any vector in terms of I, j and k components. So, I can express a vector in terms of orthogonal components, right, x1, x2 and x3. There are 3 orthogonal components, and using these 3 orthogonal components, I can span a 3D space. Okay. So, in general, what you are used to is assuming that these vectors are unit vectors I, j and k. The idea is similar, but making it little bit more generic. And we have also seen that the values of these coefficients C1, C2 and C3 is nothing but can be simply obtained by taking the inner product of vector with one orthogonal component divided by the length square of that vector, and similarly I can obtain also C2 and C3. Okay. So, what we are saying here is, in the case of vectors, you can decompose a vector in terms of orthogonal vectors, and using these orthogonal vectors you can span a given space. Remember, orthogonal vectors are always linearly independent because they are orthogonal, right. So, they are linearly independent, and if they are spanning a given space, that means they forms a basis set. Okay. So, that is important. So, you can think about the basis set. We have already seen why basis sets are important. So, you can obtain a basis set by having some orthogonal vectors in such a way they span a given space, okay, and we call this as basis vectors. Extending the same idea to signals, we can say that I can have a signal and I can express this signal as a linear combination of orthogonal signals. Okay. So, x and t denotes a set of orthogonal signals or functions, right. What are orthogonal functions? to obtain orthogonal functions, I have to take a signal, I have to take another signal from the same set. So, XMT is different from XNT in general. I have to take the inner product. So, this gives me the inner product operation between XMT and XNT, and this should be 0 if m is not same as n. That means, if the functions involved are different functions, then they have to be orthogonal. So, for orthogonality, the inner product must be 0, and hence if I choose two signals, then this expression should give me 0. However, if the signal is same as this, if two signals involved are the same signals, then what this will give me is the energy of the signal, right, because then this would be XMT into XMT conjugate dt, and this is nothing but this would give me energy of the signal, right. So, this is a test to construct an orthogonal set or orthogonal family. So, this is a big idea, constructing a signal in terms of orthogonal functions. Moreover, if this energy is always 1, that means all signals in the set have the energy as 1. This is similar to unit vectors, then we say that set as orthonormal set. That means, orthonormal set is a set where the energy of the signals involved is 1. Okay. So, that is the basic difference between orthogonality and orthonormality. In orthonormality, we have added restriction that the signal's energy should also be 1, unity. What can we choose as basis vectors? Well, there are a lot of examples that we can choose as basis vectors. We can use complex exponentials to construct these functions or orthogonal functions that we do in case of Fourier series. We will learn about this in this course. We have Walsh functions which we use for CDMA applications. We have Laurent polynomials, logger functions, Hermite polynomials, Bessel functions, Chebyshev polynomials, Jacobi polynomials, and so on and so forth. So, there is a wide variety of functions that you can choose to construct your basis vectors. Few examples, few important examples of such functions we will see in this course. Okay. So, let us see what is the energy in the error signal. So, if I have a signal x t and I am approximating it as a linear combination of n orthogonal functions, first of all we see what is the error signal. Error signal can be obtained by taking a difference between LHS and RHS. So, this is the error signal. We have done and calculated this error signal several times. This is the error signal. Energy in the error signal can be obtained simply by squaring this quantity up. So, at this moment we are assuming everything to be real. So, we do not have to worry about magnitude and so on and so forth. Now, this is of the form a minus b whole square. So, we can think about this as a square plus b square minus 2ab. So, this is what we get. Now, if you look at this expression, so this is what we have derived in the last slide, and if you see this, so we already know that the value of the nth coefficient can simply be obtained by taking the inner product of the signal with nth orthogonal function divided by the energy of the nth orthogonal function. So, now we know that this is the energy of x n t. So, this is energy of x n t. So, now I know that this is available here. So, I can replace this quantity with C n E n. Doing that, we get C n square E n. Similarly, I can see that this is also E n. So, I can replace this with E n and I get this. Now, I see that this and this can be subtracted to get this. Now, if we look at this expression, if this is a finite quantity, this will be a finite quantity if the signal is an L2 signal or L2 waveform, because L2 waveform has finite energy and this is the energy. So, this quantity is finite. Now, this quantity increases as n increases because this is a positive quantity. So, this quantity increases as n increases, and finally, you hope that as the number of terms increases, the energy in the error decreases. So, if I make n tends to infinity, energy in the error will go to 0, and hence, so starting I can write x t as summation C n x n t, at least if n is pretty large. Okay. Then I hope that the energy in the error will go to 0, and this is all about the convergence. So, I can write x t in this form, at least if n is pretty large, infinity. So, let us see the convergence. When you are writing this expression, you have to understand that the LHS is not same as RHS in point wise sense. That means, for all values of time, the LHS is not same as RHS. So, it is the equality is not in the ordinary sense, this equality is not in the point to point equality. Okay. So, LHS might be different from RHS at some time instances. This equality is in the sense of that the energy in the difference of LHS and RHS tends to 0. That means, if you subtract LHS from RHS, find the energy in that different signal, that energy in the different signal will go to 0, at least if the number of terms involved in the summation is pretty large. So, this is what we are writing. So, this is what we are saying, if I take a difference between LHS and RHS, the energy in the different signal, this energy will go to 0 if n is pretty large, and this convergence is set to as limit in the mean convergence. So, this quantity converges to this quantity in the limit in the mean sense, in this sense. Okay. So, this is the completion of the lecture 2. In this lecture, we have learned about inner projective spaces. We have learned that by using this idea of inner product, we can define the length of signals, we can define the angle between two signals, and this is a very important idea which will simplify things for us, because we know that dealing with vectors is easy, dealing with signals will also be subsequently easy. We have also seen and looked at the definition for inner product of L2 signals. We have already convinced you that L2 space is an inner projective space. Finally, we have seen orthogonal expansion of a signal. That means, you can take a signal and you can think about the signal as a linear combination of orthogonal functions. From next lectures, we will be looking at specific examples of orthogonal expansion of a signal. We will look at what is known as Gram-Schmidt orthogonalization procedure, and we will see there that the signal can be constructed in terms of finite number of orthogonal functions, and also there is no error in that approximation. So, we will start with Gram-Schmidt orthogonalization procedure in the next class. Thank you.